Chapter 6 of 20th Century Inventions, A Forecast. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Mike Ockenick. 20th Century Inventions, A Forecast by George Sutherland. Chapter 6. Ships. The cargo slave and the ocean greyhound are already differentiated by marked characteristics, and in the 20th century the divergence between the two types of vessels will become much accentuated. The object aimed at by the owners of cargo boats will be to secure the greatest possible economy of working, combined with a moderately good rate of speed, such as may ensure shippers against having to stand out of their capital locked up in the cargo for too long a period. Hence, cheap power will become increasingly a desideratum, and the possible applications of natural sources of energy will be keenly scrutinized with a view to turning any feasible plan to advantage. The sailing ship and the economic and constructive lines upon which it is built and worked will be carefully overhauled with a view to finding how its deficiencies may be supplemented and its good points turned to account. One result of this renewed attention will be to confirm, for some little time, the movement which showed itself during the past decade of the 19th century for an increase of sailing tonnage. Sooner or later, however, it will be recognized that sail power must be largely supplemented, even on the sailor, if it is to hold its own against steam. For mails and passengers, on the other hand, steam must more and more decidedly assert its supremacy. Yet the mail packet of the 20th century will be very different from packets which have made the running toward the close of the 19th. She will carry little or no cargo excepting specie, and goods of exceptionally high value in proportion to their weight and bulk. Nearly all her below-deck capacity, indeed, will be filled with machinery and fuel. She will be in other respects more like a floating hotel than the old ideal of a ship, her cellars, so to speak, being crammed with coal, and her upper stories fitted luxuriously for sitting and bedrooms, and brilliant with the electric light. But in size she will not necessarily be any larger than the 19th century type of mail steamer. Indeed, the probability is that, on the average, the 20th century mail packets will be smaller, being built for speed rather than for magnificence or carrying capacity. The turbine engine will be the main factor in working the approaching revolution in mail steamer construction. The special reason for this will consist in the fact that only by its adoption can the conditions mentioned above be fulfilled. With the ordinary reciprocating type of marine steam machinery, it would be impossible to place, in a steamer of moderate tonnage, engines of a size suitable to enable it to attain a very high rate of speed, because the strain and vibration of the gigantic steel arms, pulling and pushing the huge cranks to turn the shafting, would knock the hull to pieces in a very short time. For this very reason, in fact, the marine architect and engineer have hitherto urged, with considerable force of argument, that high speed and large tonnage must go concomitantly. Practically, only a big steamer with the old type of marine engine could be a very fast one, and for ocean traffic at any rate, a smaller vessel must be regarded as out of the running. Very large tonnage being thus made a prime necessity, it followed that the space provided must be utilized, and this need has tended to perpetuate the combination of mail and passenger traffic with cargo carrying. The first step toward the revolution was taken many years ago when the screw propeller was substituted for the paddle wheel. The latter means of propulsion caused shock and vibration not only owing to the thrusts of the piston rod from the steam engine itself, but also from the impact of the paddles upon the water one after the other. A great increase in the smoothness of running was attained when the screw was invented. A propeller which was entirely sunk in the water and therefore exercised its force, not in shocks, but in gentle, constant pressure upon the fluid around it. Such as the windmill is for wind, and the turbine water wheel for water, was the screw propeller, although adapted not as a generator, but as an application of power. Having made the work and stress continuous, the next thing to be accomplished was to effect a similar reform in the engine supplying the power. This is accomplished in the turbine steam engine by causing the steam to play in strong jets continuously and steadily upon vanes which form virtually a number of small windmills. Thus, while the screw outside of the hull is applying the force continuously, the steam in the inside is driving the shafting with equal evenness and regularity. The steam turbine does not appear to have by any means reached finality in its form, such questions as the angle of impact which the jet should make with the surface of the vane, and the size of the orifice through which the steam should be ejected, being still debatable points. But on one matter there is hardly any room for doubt, and that is that the best way to secure the benefit of the expansive power of steam is to permit it to escape from a pipe having a long series of orifices and to impinge upon a correspondingly numerous series of vanes, or, perhaps, upon a number of vanes arranged so that each one is long enough to receive the impact of many jets. Hitherto the steam supply pipe emitting the jet has been placed outside of the circle of the wheel, but the future form seems likely to be one in which the axis of the wheel is itself the pipe which contains the steam, but which permits it to escape outwards to the circumference of the wheel. The latter is, in this form of turbine, made in the shape of a paddle wheel of very small circumference but considerable length, the paddles being set at such an inclination as to obtain the greatest possible rotative impulse from the outward rushing steam. The pipe must be turned true at intervals to enable it to carry a number of diminutive wheels upon which these long vanes are mounted, and a very strong connection must be made between these wheels and the shaft of the screw. Inasmuch as high speed of rotation is to be maintained, the pitch of the screw in the water is set so as to offer but slight opposition to the water at each turn. The immense speed attained is thus due, not to the actual power with which the water is struck by the screw at each revolution, but to the extraordinary rapidity with which the shaft rotates. The twin screw, with which the best and safest of modern steamships are all fitted, will soon develop into what may be called the twin stern. Each screw requires a separate set of engines, and the main object of the duplication is to lessen the risk of the vessel being left helpless in case of accident to one or other. The advisability of placing each engine and shafting in a separate watertight compartment has therefore been seen. At this point there presents itself for consideration the advisability of separating the two screws by as wide a distance as may be convenient, and placing the rudder between the two. Practically, therefore, it will be found best to build out a steel framework from each side of the stern for holding the bearings of each screw in connection with the twin watertight compartments holding the shafting, and thus will be evolved what will practically represent a twin or double stern. In the case of the turbine steamer, several of the forms of screw which were first proposed when that type of propeller was invented will again come up for examination, notably the Archimedean screw, wound round a fairly long piece of shafting. The larger the circular area of this screw is, the less will be the risk of smashing the water, or of losing hold of it entirely in rough weather. With twin screws of the large Archimedean type, the propelling apparatus of a turbine steamer will, if the screws are left open, be objected to on the ground of liability to foul or get broken in crowded fairways. Hence will arise a demand for accommodation for each screw in a tube, forming part of the lower hull itself, and open at the side for the taking in of water, while the stern part is equally free. In this way there is evolved a kind of compromise between the two principles of marine propulsion, by a screw and by a jet of water thrown to sternward. The water jet is already very successfully employed for the propulsion of steam lifeboats, in which, owing to the danger of fouling the life-saving and other tackle, an open screw is objectionable. The final extermination of the sailing ship is popularly expected as one of the first developments of the 20th century in maritime traffic. Steam, which for oversea trade made its entrance cautiously in the shape of a mere auxiliary to sail power, had taken up a much more self-assertive position long before the close of the 19th century, and has driven its former ally almost out of the field in large departments of the shipping industry. Yet a curious and interesting counter-movement is now taking place on the Pacific coast of America as well as among the South Sea Islands and in several other places where coal is exceptionally dear. Trading schooners and barks used in these localities are often fitted with petroleum oil engines, which enable them to continue their voyages during calm or adverse weather. For the owners of the smaller grade of craft, it was a material point in recommendation of this movement that, having no boiler or other parts liable to explode and wreck the vessel, an oil engine may be worked without the attendance of a certificated engineer. As soon as this legal question was settled, a considerable impetus was given to the extension of the auxiliary principle for sailing ships. The shorter duration of the average voyage made by the sail and oil-powered vessels had the effect of enabling shippers to realize upon the goods carried more speedily than would have been possible under the old system of sail power alone. It is already found that in the manner of economy of working, including interest on cost of vessel and cargo, these oil auxiliary ships can well hold their own against the ordinary steam cargo slave. Up to a certain point, the policy of relying upon steam entirely, unaided by any natural cheap source of power, has been successful. But the rate of speed which the best types of marine engines impart to this kind of vessel is strictly limited, owing to considerations of the enormous increase of fuel consumption after passing the 12 or 14-mile grade. For ocean greyhounds carrying mail and passengers, the prime necessity of high speed has to a large extent obliterated any such separating line between waste and economy. It is, however, a mistake to imagine that the cargo steamer of the future will be in any sense a replica of the mailboat of today. The opposition presented by the water to the passage of a vessel increases by leaps and bounds as soon as the rate now adopted by the cargo steamer is passed, and thus presents a natural barrier beyond which it will not be economically feasible to advance much further. If then we recognize clearly that steam cargo transport across the ocean can only be done remuneratively at about one-half the speed now attained by the very fastest mail boats, we shall soon perceive also that the chances of the auxiliary principle, if wisely introduced, placing the sailor on a level with the cargo ship worked by steam alone, are by no means hopeless. A type of vessel which can be trusted to make some 10 or 12 knots regularly, and which can also take advantage of the power of the wind whenever it is in its favour, must inevitably possess a material advantage over the steam cargo slave in economy of working, while making almost the same average passages as its rival. Then, also, the sailless cargo slave, in the keen competition that must arise, will be fitted with such appliances as human ingenuity can in future devise, or has already tentatively suggested, for invoking the aid of natural powers in order to supplement the steam engine and effect a saving in fuel. One of these will no doubt be the adoption of the heavy pendulum with universal joint movement in a special hold of the vessel so connected with an air compression plant that its movements may continually work to fill a reservoir of air at a high pressure. The marine engines of the ordinary type will then be adapted to work with compressed air, and the true steam engine itself will be used for operating an air compressor on the system adopted in mines. The pendulum apparatus, of course, is really a device for enabling a vessel to derive, from the power of the waves which raise her and roll her, an impetus in the desired direction of her course. Inventions of this description will at first be only very cautiously and partially adopted, because if there is one thing which the master mariner fears more than another, it is any heavy moving weight in the hold, the motions of which during a storm might possibly become uncontrollable. When steam was first applied to the propulsion of ships, the common argument against it was that any machine worked by steam and having sufficient power to propel a vessel would also develop so much vibration as to pull her to pieces, to say nothing of the risk of having her hull shattered at one fell blow by the explosion of the steam boiler. These undoubtedly are dangers which have to be provided against, and probably the occasional lack of care has been the cause of many an unreported loss, as well as of recorded mishaps from broken tail shafts and screws, or from explosions far out at sea. The air-compressing pendulum will no doubt be constructed on such a principle that, whenever there is any danger of its weighty movements getting beyond control or doing any damage to the vessel, its force can be instantly removed at will, and the apparatus can be brought to a standstill by the application of friction brakes and other means. The weight may be made up of comparatively small pigs of iron, which, through the opening of a valve controlled from the deck by the stem of the pendulum, can be let fall out into the hold separately. The swinging framework would then be steadied by the friction brake gripping it gradually. Auxiliary machinery of this class can only be made use of, as already indicated, to a certain strictly limited extent, owing to the tendency of any swinging weight in a vessel to aggravate the rolling during heavy weather. Some tentative schemes have been put forward for tapping a source of wave power by providing a vessel with flippers, resting upon the surface of the water outside her hull, and actuating suitable internal machinery with the object of propulsion. A certain amount of encouragement has been given by the performances of small craft fitted in this way, but it is objected by seafaring men that the behaviour of a large vessel, encumbered with outlying parts moving on the waves independently, would probably be very erratic during a storm and would endanger the safety of the ship itself. No kind of floating appendage, moving independently of the vessel, could exercise any actual force by the uprising of a wave in lifting it, without being to some extent sunk in the water, and accordingly, when the waves were running high, there would be imminent risk that heavy volumes of water would get upon the apparatus and prevent the ship from righting itself. Many of the schemes that have been put forward, by patent and otherwise, for the automatic propulsion of ships have entirely failed to commend themselves by reason of their taking little or no account of the behaviour of a ship fitted with the proposed inventions during very rough and trying weather. The swinging pendulum, with connected apparatus for compressing air or perhaps for generating the electric current, seems to be the most controllable and therefore the safest of the various types of apparatus which are applicable to the utilization of wave power for propulsion. In the construction of connecting machinery by which the movements of a pendulum hanging up from a universal joint may be transmitted to wheels or pistons operating compressors or dynamos, it is necessary to transform all motions passing in any direction through the spherical or bowl-shaped figure traced out by the end of the pendulum in the course of its swinging. This may be effected, for instance, in the case of a pendulum working air compressors, by mounting the latter on bearings like those of the gun carriage in a field piece, and having two of them operating one at right angles to the other. The rods which carry the air-compressing pistons are then connected to the end of the pendulum by universal joints, and the parts which have been likened to a gun carriage are fixed on pivots so as to be able to move horizontally. Air-tight joints in the pipes which lead to the compressed air reservoir are placed in the bearings of this mounting. We thus have the same kind of provision for taking advantage of a universal movement in space as is made in solid geometry by three coordinates at right angles to one another for measuring such movements. Another plan is to have the pendulum swung in a strong steel collar and carrying at its end three or more air-compressing pumps set radially, with the piston rods thrust outward by a strong spring on each, but with the ends perfectly free from any attachment, yet fitted with a buffer or wheel. As the pendulum moves, it throws one or more of these piston rod ends into contact with the inner surface of the ring, driving it into the compressing pump. At the top of the pendulum there is a double or universal pipe joint through which the air under pressure is driven to the reservoir, and by which the apparatus is also hung. This is the simplest, and in some respects the best form. A very simple type of the wave power motor as applied to marine propulsion is based upon an idea taken from the mode of progression adopted by certain crustaceans, namely the possession of the means for drawing in and rapidly ejecting the water. Something of the kind will probably be made available for assisting in the propulsion of sailing ships which are not furnished with machinery of any type suitable for the driving of a screw. A very much simplified form of the pendulous or rocking weight is applicable in this case. A considerable amount of cargo is stowed away in an inner hull, taking the shape of what is practically a gigantic cradle rocking upon semicircular lines of railway iron laid down in the form of ribs of the ship. To the sides of these large rocking receptacles are connected the rods carrying, at their other ends, the pistons of large force pumps, which draw the water in at one stroke and force it out to sternwards below the waterline at the other. In this arrangement it is obvious that only the roll and not the pitch of the vessel can be utilized as the medium through which to obtain propulsive force. But it is probable that fully 80% of the movements of a vessel during a long voyage, as indicated say by the direction and sweep of its mastheads, consists of the roll. Each ton of goods moved through a vertical distance of 1 foot in relation to the hull of the vessel has in it the potentiality of developing, when 14 or 15 movements occur per minute, about 1 horsepower. A cradle containing 200 tons, as may therefore be imagined, can be made to afford very material assistance in helping forward a sailing ship during a calm. In such tantalizing weather, the ground swell of the ocean usually carries past a becalmed vessel more waste energy than is ever utilized by its sails in the briskest and most propitious breeze. For sailing ships especially, the rocking form of wave motor as an aid to propulsion will be recommended on account of the fact that when the weather is on the beam, both of its sources of power can be kept in full use. The sailing vessel must tack at any rate with the object of giving its sail power a fair chance, and thus when it has not had a fair wind that follows free, it must always seek to get the breeze on its beam, and therefore usually the swell must be taking it sideways. It would only be on rare occasions that a sailing vessel, if furnished with rocking gear for using the wave power, would be set to go nearer to the teeth of the wind than she would under present conditions of using sail power alone. The advantage of the wave power, however, would be seen mainly during the calm and desultory weather which has virtually been the means of forcing sail power to resign its supremacy to steam. For checking the rocker in time of heavy weather, special appliances are necessary, which, of course, must be easily operated from the deck. Wedge-shaped pieces with rails attached may be driven down by screws upon the sides of the vessel, thus having the effect of gradually narrowing the amplitude of the rocking motion until a condition of stability with reference to the hull has been attained. In the building of steel ships, as well as in the construction of bridges and other erections demanding much metalwork, great economies will be introduced by the reduction of the extent to which riveting will be required when the full advantages of hydraulic pressure are realized. The plates used in the building of a ship will be knocked up at one side and split at the other, with the object of making joints without the need for using rivets to anything like the extent at present required. In putting the plates thus treated together to form the hull of a vessel, the swollen side of one plate is inserted between the split portions of another, and the latter parts are then clamped down by heavy hydraulic pressure. This important principle is already successfully used in the making of rivetless pipes, and its application to ships and bridges will only be a matter of a comparatively short time. Through this reform, and the further use of steel ribs for imparting strength, and thus admitting of the employment of thinner steel plates for the actual shell, the cost of shipbuilding will be very greatly reduced. Hoisting and unloading machines will play a notable part in minimizing the expenses of handling goods carried by sea. The grain elevator system is only the beginning of a revolution in this department which will not end until the loading and unloading of ships have become almost entirely the work of machinery. The principle of the miner's tool known as the sand auger may prove itself very useful in this connection. From a heap of tailings the miner can select a sample by boring into it with a thin tube, inside of which revolves a shaft carrying at its end a flat steel rotary scoop. The auger, after working its way to the bottom of the heap, is raised, and, of course, it contains a fair sample of the sand at all depths from the top downwards. On a somewhat similar principle, the unloading of ships laden with grain, ore, coal, and all other articles which can be handled in bulk and divided, will be carried out by machines which, by rotary action, will work their way down to the bottom of the hull, and will then be elevated by powerful lifting cranes. For other classes of goods, permanent packages and tramways will be provided in each ship, and trucks will be supplied at the wharf. For coastal passages across shallow but rough water like the English Channel, the services of moving bridges will be called into requisition. One of these has been at work at St. Malo on the French coast opposite Jersey, and another was more recently constructed on the English coast near Brighton. For the longer and much more important service across the Channel, submarine rails may be laid down as in the cases mentioned, but in addition it will be necessary to provide for static stability by fixing a flounder-shaped pontoon just below the greatest depth of wave disturbance, and just sufficient in buoyancy to take the great bulk of the weight of the structure off the rails. In this way passengers may be conveyed across straits like the Channel without the discomforts of seasickness. The stoking difficulties on large ocean-going steamers have become so acute that they now suggest the conclusion that, notwithstanding repeated failures, a really effective mechanical stoker will be so imperatively called for as to enforce the adoption of any reasonably good device. The heat, grime, and general misery of the stoke-hole have become so deterrent that the difficulty of securing men to undertake the work grows greater year by year, and in recruiting the ranks of the stokers resort had to be had more and more to these unfortunate men whose principal motive for labour is the insatiable desire for a drinking bout. On the occasions of several shipwrecks in the latter part of the 19th century, disquieting revelations took place showing how savagely bitter was the feeling of the stoke-hole toward the first saloon. As soon as the mechanical fuel shifter has been adopted, and the boilers have been properly insulated in order to prevent the overheating of the stoke-hole, the stoker will be raised to the rank of a secondary engineer, and his work will cease to be looked upon as in any sense degrading. On the cargo slave steamer and sailor, a similar social revolution will be brought about by the amelioration of the conditions under which the men live and work. Already some owners and masters have begun to mitigate, to a certain extent, the embargo which the choice of a seafaring life has in times past been understood to place upon married men. Positions are found for women as stewardesses and in other capacities, and it is coming to be increasingly recognized that there is a large amount of woman's work to be done on board a ship. By and by, when it is found that the best and steadiest men can be secured by making some little concessions to their desire for a settled life, and their objections to the crimp and the girl at every port, and all the other squalid accessories so generally attached in the popular mind to the seaman's career, there will be a serious effort on the part of owners to remodel the community on board of a ship on the lines of a village. There will be the ship's shop, and the ship's school, the ship's church, and various other institutions and societies. Thus, in the 20th century, the sea will no longer be regarded, to the same extent as in the past, as the refuge for the ne'er-do-well of the land-living populace. And this, more than perhaps anything else, will help to render traveling by the great ocean highways safe and comfortable. It is a common complaint on the part of owners that by far the larger part of maritime disasters are directly traceable to misconduct or neglect of duty on the part of masters, officers, or crew. But they have the remedy in their own hands. End of Chapter 6. Recording by Mike Okonek.